In part 2 of our two-part video series on the LASSO algorithm, we'll explore an important detail. As a motivating example, consider the relationships of height with knee circumference in centimeters and age in years, plotted here. Though height is associated with both predictors, its relationship with knee is definitely stronger. That said, let's put both predictors into a linear regression model of height. A least squares estimate of the model has this formula. Height equals 50.1 plus 0.58 times knee minus 0.05 times age. Suppose instead that we estimated this model using a LASSO algorithm. We learned in part 1 of the video series that this algorithm will penalize predictors with quote-unquote large coefficients. If it hasn't already, this might raise some concerns for you. Mainly, does this penalty mean that the LASSO will get rid of the knee predictor, which has a larger coefficient than age but is clearly the stronger predictor? In short, no, but let's explore why. First, it's important to remember that our predictors are measured on completely different scales. Knee circumference is measured in centimeters, whereas age is measured in years. In turn, their model coefficients are on completely different scales, thus can't be directly compared. Mainly, what's big on one scale is different than what's big on the other. Luckily, there's an easy fix. Standardizing predictors puts their units, hence coefficients, on the same scale. Once standardized, we can then directly compare them. For example, in the plots here, knee and age have both been standardized to the same scale. They have the same x-axes, with the predictor outcomes roughly centered at 0 and falling between roughly -3 and 3. Notice, however, that changing the scales of our predictors hasn't changed their relationship with height. Mainly, everything besides the axes appears the same as before. So, what exactly do I mean by standardizing? Though you might not remember, you briefly learned about standardizing, or z-scores, in Stat 155. To calculate the z-score for some outcome of predictor x, we subtract the mean x value and then divide by the standard deviation of x values. The result then measures how far an outcome falls from the mean. Specifically, how many standard deviations an individual outcome falls above or below the mean outcome. Examples help. Let's start with the age predictor. The ages of subjects in our sample vary around a mean of 45 years with a standard deviation of 13 years. For example, consider a 58-year-old. Standardizing their age will help assess whether 58 is big or small. To this end, if we subtract a mean age of 45 and then divide by the standard deviation of 13, we're left with 1. That is, a 58-year-old falls 1 standard deviation above the mean age. Next, consider the knee predictor. The knee circumferences of subjects in our sample vary around a mean of 40 centimeters with a standard deviation of 3 centimeters. For example, consider somebody with a 43 centimeter knee circumference. Subtracting the mean of 40 and then dividing by the standard deviation of 3, we're left with 1. That is, a 43 centimeter knee measurement falls 1 standard deviation above the mean circumference. Furthermore, our standardized age and knee outcomes are now on the same scale. Luckily, though it's important to recognize the impact of our predictor scales, we don't have to worry about it when implementing the LASSO algorithm in R. Mainly, suppose we start with our unstandardized data with all predictors on their original scales. We can then feed this data into the LASSO algorithm. The authors of the LASSO code made things easy for us. Behind the scenes, this code standardizes all predictors, hence coefficients, for us. Even better, when the LASSO results are reported, the coefficients are transformed back to the original scales, making them much more natural to interpret. As we'll learn later this semester, we won't always be so lucky.